So once we get these values, we then compare either our chi-squared value or our p-value to a different value, either the significance level or your critical value. So the next question then says the critical value for this test is 5.991. And how we use this is we always compare our critical value to our chi-squared value. So I'm going to compare critical value of 5.991 and a chi-squared value of 3.83. Since 5.991 is greater than 3.83, this means that if your chi-squared value is less than your critical value, there is insufficient evidence to reject our null hypothesis. So we compare our chi-squared value to our critical value, and we compare our p-value to our significance level, which notice here that our significance level was 5%, and our p-value here is greater than 5%, which is another reason why we would not have sufficient evidence. And here's just kind of a general idea of when to reject and when not to reject. To keep in mind, I would recommend writing it at the top of your notes. So you can either talk about the chi-squared value or you can talk about the p-value. So the chi-squared value or the p-value. They both come from the same place in your calculator. When we're talking about the chi-squared value, if the chi-squared value is greater than your critical value, so for instance, what we talked about down here, our chi-squared value was less than our critical value, or if your p-value is less than your significance level, then you can reject the null hypothesis. So it's either this guy, either your chi-squared value is greater than your critical value or your p-value is less than your significance level. Either of those would result in a rejection of your null hypothesis. If you have a chi-squared value that is less than your critical value, or if your p-value is greater than your significance level, then we would fail to reject the null hypothesis. Both of those situations happened in this example, where the significance level is 5%, so our p-value is greater than 0.05, and this guy is less than our critical value. And both of those result in a fail to reject of the null hypothesis. So you have to only compare chi-squared to critical value and p to significance level. Those are the only two that get compared to each other. Do not cross ways with that. Okay, example number 2. The time taken by an 8-year-old children to solve a puzzle can be modeled by a normal distribution with a mean of 12 and a standard deviation of 2.5. The times taken to solve the same puzzle by a random sample of 50 10-year-old children are as follows. So this is a sample of children who are trying out the puzzle and how much time they took to solve the puzzle. This is a test using a 10% significance level, whether the times of the 10-year-old children come from the same distribution. So we're trying to determine whether we follow this normal distribution. So this is your goodness of fit test. Does it follow the normal distribution that we talked about? So our null hypothesis, when we're just given a blanket question like this, we're not stepped through how to do it. Notice that our previous problem stepped us through how to answer that question by holding our hand through the process, and this is going to be without hand holding. So the first thing that we did on our previous problem is the first thing that we have to do if we're not asked to do it. That you do need to state what your null hypothesis and your alternative hypothesis are, so then that way it's easy to keep things straight, because maybe as you've noticed in class, this idea of accepting or rejecting a null hypothesis can get really flipped around with just how your brain processes it. So your null hypothesis is that it's the same distribution. Everything stays the same. The distribution is the same. We can even write it in our normal distribution notation. So that's n parentheses, and then we put our average, which is 12, and then our variance, which is 2.5 squared. So then our alternative hypothesis is the distribution is not the same. Something else that we need to find out next is our levels of freedom, or degrees of freedom, and that's your V value. Remember that it's your groups in your table minus 1. We've got 5 different groups in this table. Minus 1 is 4 for our degrees of freedom. So we've got our observed frequencies. The other thing that we need, so this is kind of like your first step, is to state your null and alternative hypothesis. The second step is to determine your degrees of freedom. Your third step is to find your expected frequencies. So I'm going to make a really quick, like, short table to talk about finding these expected frequencies. So we've got our t value, our observed frequency, I'll put there, and then our expected frequency. So we've got a t-value of less than or equal to 9, between 9 and 11, between 11 and 13, 13 and 15, and then greater than 15. Our observed frequencies are 10, 11, 20, 5, and 4. So expected frequency, this is something that you do know how to calculate. So let's just take a second and think about what we already think of and know of with expected frequency, and then just apply it in this case. If we're talking about an expected value, it means that we're talking about the probability of this happening and saying, okay, well, taking into consideration the probability that this happens, and that we're talking about it with 50 kids, how many would you expect to be between or less than or equal to 9? So how you find your expected value is the probability that x equals that value or is within that range, and then we multiply it by your sample size. So our sample size here is 50. And as we talked about this before, right, our probability was 1/3 because it gave it to us. So now we're going to use our normal distribution probability to find out what this expected value is. So how we do that is that we need to go back to our calculator. Finding the probability of being less than or equal to 9 is a normal CDF distribution. Lower bound of -infinity, upper bound of 9, average of 12, standard deviation of 2.5, and it gives us the probability of that occurring right here. Then we take that probability and multiply it by the sample that we're looking at. So we're looking at a sample of 50 children, so we expect that to happen 5.75 times. Remember that with your expected values, it's okay that it's not a whole number, right? If we're talking about like the number of children who were within that time frame, it's okay with an expected or an average value for that to become a decimal, even though we're not talking about 5.75 children. Okay, so we complete this by using our normal distribution and then multiplying it by 50. So for example, for this guy, we would do lower bound of 9, upper bound of 11, average of 12, standard deviation of 2.5. Find that probability and then multiply it by 50, and we get 11.48. Go ahead and find this probability or this expected value right here. So we're trying to figure out what would be the expected value if we're looking at a sample of 50 children between 11 and 13 minutes. So first what you need to do is you need to find the probability of being between 11 and 13 with a standard deviation of 12, or sorry, with an average of 12 and a standard deviation of 2.5. We then take that probability and multiply it by the sample size. So multiply it by 50 and we get 15.54. Because it's normally distributed, we know that from the center that the remaining expected values will be the same because it is symmetrical across the average. But we can go ahead and try it again. Menu 552 between 13 and 15. Multiply by 50 and we'll notice that we get 11.48 here, which makes sense because it should be symmetric across the average. And then this one will result in 5.75. So those are all of our expected values, and that's how you find expected values, is that you take the probability and multiply it by the sample size. We did it here as well. We took the probability and multiplied it by the sample size, and that's where our expected values come from. Okay, so first we state our hypotheses, then we find our degrees of freedom, then we find our expected values, and then the last thing that we do is we plug this all into our calculator, observed frequencies and expected frequencies. Right here. So I'm going to escape back to my statistics list and plug in the values that I have. Go ahead and do this on your own and tell me what you get for chi-squared as well as your p-value. For our chi-squared value, you should have gotten 8.63. For our p-value, you then get 0.07099. So that's your p-value and then your chi-squared. We are testing whether the times of 10-year-old children come from the same distribution. So we've got a chi-squared value right here and a p-value right here. And we want to know whether or not we reject the null hypothesis. And since we only have a significance level, we then compare our p-value to the significance level, which is 10%. We know that 0.07 is less than 0.10. And this means, looking back at our table, if your p-value is less than your significance level, then that means that you can reject your null hypothesis. This means the distribution is not the same. There you go. You've just run your first fully completed chi-squared test. So there's multiple steps that go into it. Stating your hypotheses, finding your degrees of freedom, finding your expected values, then finding your calculator values, and then being able to take those calculator values and create a conclusion from them. There's a lot that goes into it. So just baby steps. We're going to keep practicing.